No question from my side. Very
Thank you.
well explained. Thank you.
Thank you.
Okay, thank you, sir. So next in line for presentation is Mr. Bhavuk Kalra.
Hello. Is my video audible?
You're visible and voice is audible. Please share
Yeah,
your
great.
screen.
So I'm just starting my screen share. Let me know if you can are able to see it.
Yes, screen is visible. Please go ahead.
Great. So let me pull over the slide as well, and let me know if it's changing while I'm moving in the slideshow. Give me a moment. It's changing.
Yes, it's changing.
Okay, great. So everything is working fine. Also, just to check that if the marker is available on the screen that I'm writing.
Yes, marker is also available.
Great. So first off, thank you everyone for giving me this opportunity to present my paper titled Generalized Agent for Solving Higher Board States of Tic-Tac-Toe Using Reinforcement Learning. So first off, let me cover the agenda for this. That why this paper was introduced or why we are covering this paper today. So there are many techniques for 3x3 board of tic-tac-toe. For example, some of them are listed over here as well. So Q-learning, min-max algorithm, and QL algorithm, which are implemented and also explored in the past for solving 3x3 states of tic-tac-toe. But in this study, what I'm trying to explore is, can we make these studies more generic? Can we have like a single algorithm with little bit of tweaks here and there and present it to the higher board sets of tic-tac-toe, which is 3x3, 4x4, or 5x5? So this is very a beginning study, which is morely kind of an exploration phase, and the results which will be shared in the end of what the exploration and what the techniques used for this ideology was as well. So the existing system, I like to take you back to 2018 when Google DeepMind came in with its state-of-the-art AlphaGo. So AlphaGo is a very advanced reinforcement learning algorithm that they made, which could beat even the highest of the stock engines that we had, Stockfish. But the limitation for that was that the source code was never made public. Only 20 games were released, and the just audience is just pondering over what the algorithm could look like. The latest that we have gone is Leela Chess, which is a community-based, you could say, reinforcement learning board games playing simulation. But that is also very community-based, and we can only make approximations at this point. So this is also an attempt to that. So for select, this is actually defined as a well-posed problem. So whenever we look at board games, they're always, I'm trying to define them as well-posed problems. So well-posed problems have 5 characteristics at main. So there is a task. So task is here playing the game of tic-tac-toe, and there is a performance metric, which is the number of games won by the agent, and there is also experience as well, which is the number of games played by the agent against itself. So how the well-posed learning problem statement is defined: if you can do a task T and with the experience E, the performance is going up. That is explained as a well-posed problem in the world of board games. So for defining a board game, I like to take you back to 5 points here. So how the algorithm is defined here. So choosing first the training experience that we just discussed about. So we can have the direct training experience or indirect training experience. Direct training experience is when you have a board state. For example, this is a sample board state X0, and you give alongside the best move for this alongside as well. So X0, and for example, the best move is here, trying to make the cross here. There is direct feedback. The problem with direct feedback is that you need to implore the rules of the game alongside it. But in this ideology, indirect feedback is employed, that only the rules of the game is given. Rest all, that if a state is winning, the agent have to decide for itself. Now, next is for the algorithm is selecting the target function. So we are having that if the agent wins a state, this is a one state, we're giving the utility value of plus 100. If the agent lost a state, we are giving the utility value of plus minus 100. And if there is a game drawn, the utility value will be of that board state will be 0. And now we have defined the target function of the final board state. So what happens if we are in the intermediate of one of these board states? For example, this game is neither end nor draw. This is in between. So how do we compute the utility value for this board states? So for this is where the variable part comes into the picture as well, that some minor tweaks are required for going to the higher board state. So for the 3x3 tic-tac-toe, these are the board states that we have defined. Like these are the categories that we have taken for kind of intermediating that if a board state is preferable or not. So let me just zoom over here and take you through this slide. So we are taking the features as the following. We are taking x1 as a utility, x1 as a feature, where we are checking how many x's are in a row and how many x's are in a column. If there is single x in a row, then we are counting how many of these are in the matrix. Similarly is x2. We are checking how many O's are in a row, single row O's. And for x3, we are checking how many consecutive x are in a row. Consecutively, we are also checking how many O's are in a row. So like this, we have defined 6 parameters. Out of these 6 parameters, we have also have O and XS. That is the winning state for the agent. Using this, we are also computing the intermediate training values for this. So we have defined all the feature vectors here, and these are all the weight vectors that will come out of the training. If you do a dot product of them, we have defined a linear function that is used for calculating the intermediate board state. What is the probability of having a win in that state? Mind you that this function can also be quadratic and cubic as well. For imploring the simplicity of the algorithm, because this is a very starting state, we are keeping it as linear. So I hope that is clear. Now let's go back to the presentation slides. Now the target function is defined, and we have also defined a little bit of algorithm and the feature vector that we are going to use. This is just one of the slides that presenting that this is all is presenting the x0 feature vector, and this is all presenting the x1 feature vector. No, this is the x6 feature vector, the last one. It is very logical to sense that the agent should try to minimize this state, which is 0 in all, and maximize this x, assuming that the agent is playing x and is playing first. Okay. Yeah. So the methodology used in this case is of a well-posed problem. And there are 4 components in this, which is an experiment generator. For in this case, experiment generator is what gives us the new board states to try out. For in this case, we are only having a 3x3 tic-tac-toe, which is empty in this. You can also have a randomized state, but for the simplicity purposes, we are having an empty board. The second second group of the algorithm or the architecture is a performance system. So what a performance system does, whatever state you got, it will make the best move according to that state, whatever feature vector you have currently, and will give the solution trace of the game tree. So what game was played and what the end result was. That is the performance system for you. The next is a critic. What a critic does is implodes the feature vector values onto those board states. So now that you have a training example, so this also gives me the opportunity to explain to you what is a training example. The games played against itself are represented in the form of a training example. So training example is you could say a vector of 2, which will have the board state. For example, this is a board state, a sample board state, and it is currently favoring x in this situation, that because x is going to win in this. And there you have the utility value for this as well. For example, the utility value came out for this as 52 in the favor of x. So this is a training experience that the agent is using. After you got all the training examples with you with the utility values, you will try to hypothesize what the ideal target function should look like, what the ideal weight vector should look like. So this is the role of generalizer. Once you have some idea of how the feature vectors should look like, there again is a new experiment generated, then there is again game played, then the again feature vectors are optimized using least mean square algorithm, least mean square optimization technique. Least mean square could also be termed as the sto stochastic gradient descent optimization. So you have a stochastic trying to guide the gradient descent of the algorithm. So this, you can just explore this as many times as you want. You can play as many games as you want, which will be sharing the result as we move on. So this is the class diagram for the proposed architecture. You have which was implemented for this. You have the experiment generator. You got the generalizer. You have the roles of the performance system variable defined, and you have got the global player with the moves defined that it will be played, the function that it can utilize, and you have the function of critics as well. Because of the lack of time, we'll not be going deep into it, but we have listed down all the functions that we are currently utilizing here. So this is the overall algorithm that we are employing. Mind you that the input is the number of training samples. So number of training sample is how many games you want to train the agent over. Do you want to train it over 100? Of course, the accuracy will be less. Or do you want to train it over 50,000? So this is the input that you have to give to the agent. Of course, number of games played will increase the accuracy of the agent, but down the line. For this algorithm, we are initializing the weight vector as 0.5, 0.5 for all the feature defined. With the number of the feature that we defined earlier, the number of x's in one line and the number of x's in zero line. So those are all defined to be 0.5 in the initial case. Training games count is 0 because we have, apologies. Training games count is 0 in the initial case, and number of wins, loss, and draws we are also counting at the end. So this is the above architecture only, just playing the game against itself, optimizing the weight values. At the end, you return the weight vector, the final optimization weight vector, the number of wins, lose, and draws. Now we'll be comparing the results after the number of games played and the results that we got. So this is a table explaining the results that we got. If you train the agent over 1,000 games, the number of wins got was 761, 82, and 157. Out of which the win draw ratio was 4.85. So win draw ratio is the matrix that you can check how the agent is performing for you. And the similar are the results for the other games played as well, 1,000, 100,000, 20,000, and we go on until 1,50,000, and the number of wins, loss, and draws are given here. And the thing to note here is that win draw ratio is continuously improving as you play the number of games, and the feature vector we can also observe here as the games were played. Mind you, you can observe that the agent is trying to make sense of the W6 feature vector that we defined, which is number of O's in one line. So it is trying to minimize it. So you can say that minus 115 was the initial one, then it is trying to minimize it with minus 208, minus 175. So the agent is trying to negate that possibility altogether. It is trying to destroy whatever the opposing agent is trying to do it to him. So this is just a plot giving us an overview of what the previous slide showed. You can see that with the number of games played, the win draw ratio is improving, you can say almost linearly. And this is the implication of the weight vectors with the number of games played. You can see the weight vector defined here, W6, which is down the line very constantly. So it is just remaining down the line. And the W0, and that the 0 should be in one place, is at the upper side. So in the conclusion, that this is a very beginning study, and this attempts to give a base implementation to idea of generic solvability of tic-tac-toe. So the win-draw ratio is also very plausible in this, that we can see a linear curve that it's improving with time. So to how can we extend it to the future board states is that if you have the feature vector defined here, that you need to make very few tweaks in your code. Let me just bring up that slide again. Yeah, you need to make very few tweaks in the feature vector that you are considering for extending it to higher board states as well. We can observe that only with the linear approximation as well, we are getting very plausible results in this. So higher board state will have more feature vectors to this, and we also found in the study that we didn't include in the conclusion, some of these feature vectors might not be required as we went further down the line. So this is just a very beginning study on this, that how can we make the agent more generic. That is the end. If you have any questions, do let me know. If you want any points to be explained further, do let me know. That was all about for the presentation, and I think the rest of the slide is yeah, there is an appendix as well, that while the game we were training the agent. These were some of the sampled games plays against itself. So you can see the figure 19 on your side, that there was an exploit. So this is just for reference purposes, that there is after the 500,000 games played, that the agent resulted in a win in this situation, and the agent resulted in a draw in the another case. So this is just the work of performance metrics and the critics at your side. So this is just for reference purposes that we have added here because of the limitation of the number of slides allowed. So do let me know. So I'm open to questions now. Thank you.
Yeah, so very well explained, and no queries from my side. Thank you.
Bhauk, I have one question. Which optimizer you have used in your presentation, I mean, implementation?
So we have used the least mean square optimizer, sir. So the least mean square optimization looks something like this. So I have noted it down here as well. So if we have a feature vector wi, you can optimize it using the existing value plus eta. So it is the training rate. So it is usually 0.4, 0.3 in our case. And you have v train and minus v cap b into xi. So xi is the feature vector value, and this is the error in your case, in our case. Because of the least mean square error, this came like this, where v train, wait a minute. So v train is the ideal scenario, and v cap is our approximation scenario. So this is how the optimization is happening at the end of the stage using least mean square.
Okay. Have you implemented Adam optimizer?
Yeah, that is a possibility, sir. As I already mentioned, we have only tried because this is very beginning to the phase of the exploring of the generalized system. We are only exploring least mean square, and we have also kept the learning function to be very simple, which is a linear one. Adam optimizer is also one of the ways that we can explore it with, but haven't been tried in this study yet.
Okay, no problem. Okay, good.
Okay, Bhavuk, are you able to hear me?
Yes, Mr. Kunal.
Yeah, this is Mr. Kushal Kumar here. Okay, so I have a few questions from you. I want to ask you whether least mean square is optimizer or it is a loss function.
It's a loss function basically, sir. So least mean square looks something like this. We are also
it is optimizer or loss function. You said it is a loss function, right? So what optimizer you have used in your research?
So it's a stochastic based optimizer, sir. So what do you?
It is a loss function, and you are talking about stochastic optimization. You are talking about stochastic optimization. So there is going to be some optimizer. So can you name that optimizer that you have used in your work?
Yes, sir. Gradient descent, sir.
Gradient descent. Okay. So which package you have used for implementation of this? Have you used GIM?
Sir, GIM
have
package.
You used GIM? What
no,
you
sir,
have used
code is available on Collaboratory. The whole code was made from scratch only.
Okay.
I haven't used any package for this.
Okay, you haven't used. You have written everything like
Only the
environment,
Python,
state.
I think only the Python code. Even the, if mind you, sir, the even the least mean square and the error codes and the error logic, which is something like vtrain minus the initial one squared, is
Mhm.
also written from scratch.
Okay, okay. So you have written everything from scratch. So have you used Markov decision process somewhere?
No, sir, we haven't.
Okay, no other questions. Thank you. So, Sachin, cheers. Do you have any other further questions?
No, sir. I think he has very well explained all the queries, and I have no
Okay,
further queries. Thank you.
Okay,
thank
no
you.
question.
Okay,
Thank you, Mr. Kushal, and apologies for not naming your name correctly.
okay. So next is Umang Rastogi. Is there?